Now we're given a situation where we know initial angular velocity, final angular velocity, and time interval. What can we determine from these quantities? Well, I'm mapping this out, diagram here. People very quickly told me that if we know omega naught and omega f, we can find delta omega, and gratifyingly told me that we could also find omega bar, the average angular velocity. And the expressions are simple enough. Delta omega is just omega f minus omega naught. Omega bar is omega f plus omega naught over 2. I hope those are legible. Then what can we do once we have this information? Well, we can combine each of these with delta t. The delta omega combined with the delta t will give us the angular acceleration alpha. We simply divide delta omega by delta t, as we did in our first example. And in symbols, that's going to be delta omega, which is omega f minus omega naught, divided by delta t. That's going to be our value of alpha. And then if we put average angular velocity together with the time interval, we're going to get the angular displacement. We just multiply the average angular velocity, omega f plus omega naught over 2, by delta t, and we get delta theta. This leads us to two equations. And before I read the equations to you, you can read them yourself. Let me just point out that every bit of reasoning we've used here is completely the same as the type of reasoning, or the details actually of the reasoning, except for the units that we use in reasoning out uniform acceleration. There's nothing new in the reasoning process at all. Nothing new in the application of these things. The symbols look a little weird, and it takes a little getting used to, but your omegas are just like velocities, your theta is just like a displacement, a delta s, and delta t is a delta t. And acceleration now is, angular acceleration is alpha. Okay, well anyhow, our delta theta equals omega f plus omega naught over 2 times delta t. Omega f is omega naught plus alpha delta t. And from these two equations, we can eliminate delta t to get the fourth equation, which is completely analogous to the fourth equation of linear motion. Instead of angular velocities, we have velocities, so we can replace the omegas by these. Instead of a delta s, we have a delta theta. We could replace that by delta s, replace the alpha by an a, and we would have our fourth equation for uniformly accelerated motion along a straight line. Okay? Again, because all the reasoning steps are identical. We could then eliminate omega f from the first two equations to get the third equation, just as we did from the first two equations for linear motion to get the third equation for linear motion. And we now have four equations that apply beautifully to situations in which we have uniform angular acceleration.